If we think of integration as anti-differentiation, meaning the reverse process of differentiation, then we have to go back to the differentiation and see what sort of result we get for, say, differentiating sine bracket ax plus b. So the result will be cos bracket ax plus b. But when I differentiate what's in the bracket, then I get a. So that becomes the multiplier. Now, if I want to apply anti-differentiation, meaning the integration of this result, I will get back this. So meaning, if I just integrate a cos bracket ax plus b with respect to x, then the integration of the cos will give me sine. So I have a sine bracket ax plus b, but I would have to divide it by the result of differentiating the angular expression. That will just be a. And because this is an indefinite integration, I have to include a arbitrary constant, c. And you can see, by cancelling the common factors here, I have gone back to the original expression, sine bracket ax plus c. You can see it there. Now next, when I differentiate with respect to x of cosine function, I get a negative sign. So I have negative sine bracket ax plus b. When I differentiate the angular expression, I get a. That becomes the multiplier. Well, when I integrate negative a sine bracket ax plus b with respect to x, this is what I get. Now, when I integrate sine, I get negative cos. So if I get a negative cos, I already had a negative, so that will be positive. So I have a cos bracket ax plus b. Then I would divide it by the result of differentiating ax plus b. I get an a there. Because this is indefinite integration, I have an arbitrary constant. Again, when I do the cancellation of the common factors, I get back the original expression, which is cos bracket ax plus b. Next, differentiating the tangent function with respect to x, I get secant squared. Secant squared and the expression of the angle. So if I go the reverse way, meaning integrating this with respect to x, well, I get tangent. Oh, by the way, I must have a multiplier here. When I differentiate this, I get an a, which I'll put right in front of secant squared. And when I integrate a secant squared bracket ax plus b with respect to x, I will get tangent bracket ax plus b. This will be divided by the result of the differentiation of the angular expression a. And I have a constant right at the end. Well, the cancellation of the common factors, the expression now is reduced to tangent bracket ax plus b, which is the original expression I started out with for differentiation. So, basically, when I integrate cos to sine, integrate cos, I get sine. Integrate sine, I get negative cos. Integrate secant squared, I get tangent. Now, we are looking at the further integration of trigonometric functions. It can be made easy, sometimes with the use of trigonometric identities. And this is one of them. Now, if I have to integrate a trigonometric function that is squared, and I have to think of a way to get back to secant squared theta in this case. So the way to do it is to make tangent squared theta the subject. If I do that, I will have secant squared theta minus 1, which means here I have secant squared theta minus 1 when I integrate secant squared, I get tangent. So tangent bracket ax plus b over, when I differentiate this, I get a. Then I also have the arbitrary constant c. We are now looking at c, the use of double angle formula. Now, cos 2 theta equals to 2 cos squared theta minus 1. Well, if you look at a certain question like this, where I have to integrate with respect to x cos squared, well, I'll have to go back to this equation, rearrange it. So if I want to make cos squared theta the subject, it's a matter of rearranging this equation. So I would transpose the minus 1 to the side of cos 2 theta. And I would have to divide both sides again by 2. So this expression can be rewritten as cos. Now I have to double this angle. To do that, multiply 2 to it. I have 2ax plus 2b, then plus the 1 over 2. So this is how we can actually make it possible to integrate the expression. Well, over here, I have cos 2 theta equals 1 minus 2 sine squared theta. If I have a case like this that I have to integrate the square of the sine expression, then I will have to go back to this equation here, or the identity, make sine squared theta the subject. Dividing throughout by 2, I have 1 minus cos 2 theta over 2, which means I have to replace this expression by 1 minus cos, double this angle, I have 2ax plus 2b. Whole expression divided by 2, and then integrate with respect to x. So if you just split up this expression into the two parts, cos, the angle, divided by 2, plus half. Then when we integrate cos, we get sine, basically, and then the half will become half x. Now we look at D, the use of vector formula. And this is given to you in the first one. A, we have sine A plus sine B equals to 2 sine, the sum of the two angles divided by 2, and then cos, the difference of the two angles divided by 2. So normally, if this is to be used, then in the question itself, I would have either A sine sum of the angle divided by 2, cos difference of two angle divided by 2, or some other arrangement, maybe a fractional expression here. Yeah. So the way to deal with this would be to string this back into this. So I will have sine. Now you notice that this is basically A. If I correspond to this is the B. And then this is the A again. This is the B. So when I change this or replace this expression with what's there, I will have sine AX plus sine B with respect to x. And this is just a constant. So when I integrate this, I get negative cos AX over A. The A is obtained when I differentiate the AX. And remember, integration of sine, I'll get negative cosine. This is a constant. So when I integrate that, I'll get a constant with the x. So x sine b. Then plus the arbitrary constant, because I'm dealing with indefinite integration. The next factor formula will be sine A minus sine B. And I will have 2 times cos, the sum of the two angles divided by 2, sine, the difference of the two angles divided by 2. This expression, if I integrate it, will give me, now this expression, when I integrate, I'll find it difficult, but I have to change it to this expression first before the integration. So in this case, I will have sine AX minus sine B. That is just replacing this, which is impossible to integrate, to this expression. So the integration of sine will give me negative cos. So I have negative cos ax over, I differentiate this angular expression, I get a. This is a constant, so I have negative x sine b plus the arbitrary constant c. Now let's look at the next one of the factor formula. When I have cos A plus cos B, this is what I have. 2 times cos of the sum of the angles divided by 2 times cos, the difference of the two angles divided by 2. Again, if I have to integrate this, then it's near impossibility. Then the way out is to replace this expression by that. So integrate, that will become cos of ax plus cos of the b. Integrating cos, I'll get sine. So sine ax here over the result differentiating ax, I get a, so that will be the divisor. That is a constant, so after integration, that will be just x cos b plus the constant, the arbitrary constant c. Another factor formula would be cos A minus cos B. I will have negative 2 sine, the sum of the two angles divided by 2, times sine, the difference of the two angles divided by 2. And this expression is similar to this. All I need to do is to be replaced by a corresponding expression that is similar to this. So I have cos ax minus cos b. So to integrate cos, I will have sine. So the sine ax divided by the result of differentiating ax. This is just a constant. The integration will give me x cos b, then plus the arbitrary constant c. Now the mistake we can make is that failing to recognize that as a constant, then we integrate it, to make it sine b, then divide by a 0. Because when you differentiate a b, you get a 0. The whole thing will become undefined. So we have to recognize cos b is a constant. Now part E, we are looking at compound angle formula. So the first one there, sine A plus minus B, I will have sine A cos B plus minus cos A sine B. If I see an expression like that in my integration, this is what I'll do. I will reduce it to a form of sine bracket A plus minus B. So in this case, it would be sine bracket AX plus minus B. When I integrate this, then I will get negative cos bracket the expression of the angle divided by, when I differentiate this expression, I get A, and then plus the arbitrary constant. So from some expression like this, so long and complicated, if I can relate to this compound angle formula, the expression that I actually have to integrate is a simple one. Next, compound angle formula, cos bracket A plus minus B, I should have cos A, cos B, minus plus sine A, sine B. Now, if this expression is the one that I have to integrate, then watch out for the sign here. Now it's switched to plus minus. Then the expression that I can compress to would be cos bracket AX minus plus B with respect to X. Well, integrating the cos, I will have sine. So I have sine bracket AX minus plus B over A, which is the result of differentiation. Differentiation of the angular expression. So I will always have to include the arbitrary constant because this integration is the indefinite integration. The last of the compound angle formula, well, tangent A plus minus B, I'll get this. Tangent A plus minus tangent B divided by 1 minus plus tangent A times tangent B. Now, if you have not already asked the question in your head, why plus minus? So this is actually two formulae in one. Let me explain. Tangent A plus B will certainly give me tangent A plus tangent B divided by 1 minus tangent A, tangent B. So what we do is to read the sign on top first. Then for the second one, we read the sign below. So when I deal with a general results, I put it together instead of splitting them. So for this one, I will have the integration of tangent bracket AX plus minus B. So to integrate tangent, I must have some other results to go with. For this particular case, we stopped here, but just to look at how from here we can generate this result. So when we have to integrate this, we go back to integrating this. So somehow the result will have to be given to you before you can proceed to the next step. And questions like that will actually have that result for you. Now the R formula. So whenever you have two trigonometric functions split up by a plus or minus operator, then we have to think of ways to actually group them into one. And with the one, it's easy to integrate. For instance, if I have this, I will have to reduce it to R sine bracket theta plus alpha. By the way, the R is obtained simply by taking the square root of a squared plus b squared. And the alpha over here is the inverse tangent of b over a. b over a. So you can see those values r and alpha can be actually worked out. And in this case, we treat them as constant. So these two are just constants. So when we integrate these functions, we think in terms of just the sign. So integrating sign, we have negative cos. So negative r cos. And the angle over, when I differentiate the theta with respect to theta, I get 1. So plus c, the arbitrary constant. Next, when I have a sine theta minus b cos theta, I will have r sine bracket theta minus alpha. It will follow the sign. Negative, negative. Positive, positive. That is if the two terms involve sine first, then cos. Sine first, then cos. So that expression can be simplified to r sine bracket theta minus alpha. Integrating sine, I get negative cos. So I get negative r cos bracket theta minus alpha over 1, because I'm differentiating theta with respect to theta, plus the arbitrary constant c. Now we look at the third one of the R formulae, where I have a cos theta plus b sin theta. I will have r cos bracket theta minus alpha. So you notice that the cos theta comes first before the sin theta. So we will have the cos. So to change this into something simpler, something that is of just one trigonometric function, then we rely on this R formula. So I get R cos theta minus alpha. So to integrate cos, I get sine. R sine bracket theta minus alpha over 1 in this case, because when I differentiate the theta, I get 1. Then plus the arbitrary constant. For part D, you see the cos term comes first, so R cos bracket theta plus alpha. Now, if this is a negative, this will be a positive. If this is positive, then it will be negative there. So this is unlike the two cases beforehand, when the sign comes first. Then the operator, whether it's positive or negative, will follow. So this one can be reduced to R cos bracket theta plus alpha. So integrating cos will give me sine divided by theta divided by the differentiation of theta. That's 1. Now, with the R formula here, and also the factor formulae, and together with all the other things that was mentioned beforehand, it will help us integrate what seem to be complicated trigonometric functions easy. We come to the end of this video.